Okay, so we're going to be looking at n non-interacting particles, each with only 2 energy levels with spacing epsilon. All right, so let's call those E0 and E1, okay? And basically we can kind of call where our 0 is here. So I'm just going to call E0 as 0 and E1 as epsilon. All right. Another way, I mean, you could just use like an E and an E plus epsilon as well, but we'll just call this level 0, okay? All right, so we have n non-interacting particles with only 2 energy levels, 0 and epsilon. So what is the average energy of the particles at temperature T? All right, this is a canonical ensemble type problem, and basically we just have kind of a weighted average using the Boltzmann factor as the weighting. So if we look at the average energy, okay, we're going to sum over the energies. Okay, I'm just going to write E sub n here under the sum, okay? And then, so we multiply that by the energy, multiplied by e to the minus en over kBt. All right, and then in order to normalize this, we have to divide by the partition function, which is just this without the e, so the thing that we're taking the average of. So just without the e, so okay, so the reason we're using a sum and not an integral is because there's just 2 discrete states here. So here we go, it's nice and easy for us. All right, so the first term in our sum is 0, right, because we set, okay, so we're going, these sums are from n equals 0 to n equals 1, all right? I don't know if this, maybe I should have just wrote an n down here equals 0 to, I'll just write it up on top, n equals 1. Okay, all right, so our first one, let's just write it out. The E sub 0 is 0, and then e to the minus 0 over kBt. Okay, and our second term in this sum is epsilon is the e sub 1 is epsilon. We've done e sub 0, now we're doing e sub 1, epsilon times e. All right, again, now we have an epsilon up here, so e to the minus epsilon over kBt. All right, now we're doing our partition function here on the bottom to kind of normalize. So the Boltzmann factors give like the relative probabilities of these 2 states, but in order for, the probability of all of them to add up to 1, that's why we divide by this partition function. And so then multiplying each of these energy values by their probability weighting gives us the final average. So it's just a weighted average. So down here, it's just the same thing without the e's. So we have without the energy e's, all right, this big E. All right, so we have an e to the minus 0 over kBt plus e to the minus epsilon over kBt. All right, and again, this is the average energy per particle, okay? So when we want the average energy for the whole collection of n non-interacting particles, we'll just multiply this by n. Okay. All right, so this one goes to 0. We multiply by 0 here, right? So on top we have an epsilon e to the minus epsilon over kBt. And then this e to the 0 is 1 plus this e to the minus epsilon over kBt. Okay, so this is our average energy per particle. If we want the, I guess, maybe if we're talking about U, I don't know. If we're talking about U, maybe we're talking about the energy of the entire gas, right? So we're going to multiply this by N. So now we have the average energy for the entire gas. All right, or whatever system this is, if you want to call it gas. So here's the average energy of the particles at temperature T. So now we want to know the limit of this at high and low temperatures. All right. So for high T, let's see if we have room for this. I'm just going to draw a couple little lines to keep this separate. So what happens at high T? These T's are here on the bottom, meaning these exponents here become very small, and the exponentials, these parts, go almost to 1. Basically, they'll tend, as T goes to infinity, these go to 1. So we end up with a, writing kind of small here, but epsilon multiplied by 1, right, over 1 plus 1. So at high T, we get the average energy. Oh, and again, for the whole gas, we multiply this by N, right? So we have N epsilon over 2 at high temperature. So as you have a high temperature, it's not like all the particles don't go into the upper state. The best you can possibly do for positive temperatures anyway is to get half of them into the top and half stay in the bottom. You're maximizing the entropy there, that's the most probable configuration, and you have enough energy to make it happen. So you end up with right, epsilon over 2, 1/2, halfway between these two levels when you take the actual average and multiply that by N for the whole gas. All right, let's see if we have enough space here for low T. Okay, so what happens at low T? For small t, this exponential term, it goes like to infinity almost, right? E to the minus, so it's almost going to 0, right? So, all right, so upstairs in the exponential, this term goes, t down here becomes very small, so this term becomes very large. When we take the exponential of that, then it becomes very small. All right. So basically, let's see what we have. We have roughly, we're just going to end up with this term divided by 1. No, sorry. Not sure what I'm talking about. When we like, this becomes, so this, basically these go to 0. Okay, long story short, 0 and 0. So we have a 0 multiplied by epsilon and then divided by 1. All right, I don't know why this took so long. So for low t, basically, this is going to 0. We had a 0 on top end. All right, I think the reason I got confused is originally when I worked this out, I didn't call this lower state 0, I just called it e. So, and maybe that's more illustrative because the only reason this is 0 is because we called this 0 here. The essence of what's going on is basically we don't have, at very low temperatures, all of the particles drop down into this lower state. So it's a little confusing. Maybe I should have called this an E and an E plus epsilon up here. But as long as we get the idea that if I had written a big E here, then this would be a big E here. All right. So the reason it's going to 0 is because I wrote 0 right here. All right. The story is all the particles are dropping down into the lower state. So at very high temperatures, you get only half of them go into the excited state and half stay in the lower state. At low temperatures, there's not enough energy to kick any of them up into the excited state, and you get fewer and fewer down, and basically you end up with at t equals 0, you end up with all of them down here on the lower energy level.